last video, we were looking at using the equation delta H equals mass times temperature change times specific heat to calculate energy transfers. The problem with that equation comes with situations like here, 1 and 2. What if you don't have a temperature change? How many kilojoules of heat will it take to melt 50 grams of ice? Nowhere in here do I see temperatures. I see my mass, ice is a solid, it has a specific heat value, but there's no temperature given. Ah, you're right. Do you remember that at a phase change, there is no temperature change? So for example, we had those graphs that were like solid melting, liquid boiling, gas. When we are at the melting phase change, there is no temperature change, but yet energy is being added. It's just being used to overcome the intermolecular forces. That's what's occurring during the melting process. So you can't use that equation. As much as I love that equation, mass times temperature change times specific heat, you can't use it during a phase change. So if you don't see anything with degrees Celsius, you cannot use that equation, and instead look for a word that represents a phase change. I bet we're doing a phase change if you don't see a temperature change. How many kilojoules of heat would it take to, yep, here it is, melt 50 grams of ice? For melting, we use this equation. Melting is moles times heat of fusion. And it's an easy equation to use. So you look up heat of fusion on a chart. Here she is. 6 kilojoules per mole for water. By definition, that means that it takes 6 kilojoules of energy to melt 1 mole of ice, solid water. Well, what if you have more or less than a mole? Then you just multiply by the amount of moles that you do have. Okay, this isn't so bad then. So we do need to calculate moles. I need to take this 50 grams of ice, which is solid water, and we need to get it out of grams and into moles. You'll never escape the mole, right? 1 mole has the mass on the periodic table, a little over 18. And so we'll divide, and maybe if we leave 3 sig figs, we'd be saying 2.77 moles. Alright, so yeah, you got to calculate moles, but now it's just plug and chug. So now to calculate delta H, I have my 2.77 moles, and we multiply by the heat of fusion, 6 kilojoules per mole. It takes 6 kilojoules to melt 1 mole. I've got almost 3 moles. So it kind of makes sense. We're going to multiply. We'll multiply across. We'll leave a couple figures. I guess I could keep it consistent. 16.6 kilojoules. Now this one comes out in kilojoules because my constant is in kilojoules. So really what you have is like moles times kilojoules per mole. So the mole is going to cancel. And then your final unit is just the kilojoules. So the unit will depend on the constant. Often specific heat values are just given in joules, and then our final answer comes out in joules. Here, the heat of fusion values are given in kilojoules, so my answer is in kilojoules. That didn't hurt so bad. Now look at number 2. This one's kind of interesting. What is the energy change that would result when 154 grams of mercury freeze to become a solid? That'd be kind of interesting. I guess you could freeze mercury. It's a liquid. So again, I don't see any temperatures. There is no degrees Celsius. But instead I see a phase change. Freeze. Now the problem is there is no such thing as like heat of freezing. Heat of fusion is defined as the amount of energy it takes to melt 1 mole. Melting is an endothermic change. So we should always get a positive delta H. Well, guess what? Freezing is the same change, it's just the opposite direction. It's still the change between a liquid and a solid, but now we're going to remove energy to freeze something. So the freezing process is exothermic, which means we should have a negative delta H value. You can use the heat of fusion. We're just going to make it exothermic, or negative. So for example, like in number 1, I would have to add 16.6 kilojoules to melt 50 grams of ice. If I want to freeze 50 grams of liquid water, I would need to remove 16.6 kilojoules. Same quantity of energy, the difference is just the direction of the energy flow. So I still need moles. I have 154 grams of mercury. I need to cancel grams and get it in moles. 1 mole of mercury is about 200.59 grams on my periodic table. So with 3 sig figs, I'm at about 0.768 moles. And now here's all we got to do. Delta H equals. I'm going to go and look up the heat of fusion. For mercury, 2.29 kilojoules per mole, but that's in the endothermic direction if I wanted to melt the mercury. I want to do the opposite, so we'll just make it negative. So we'll go negative 2.29 kilojoules per mole, but I have 0.768 moles. You could put this in either direction. I could go moles times opposite heat of fusion. Doesn't matter. I'm just going to plug it all in my calculator. And so I'll say negative 1.76. And again, this would be in kilojoules. Exothermic. And that is totally fine. The freezing phase change should release energy from the particles. So these are the same equation. So technically for melting, we go moles times heat of fusion. But if you want to do this for freezing, you would just say delta H equals moles times opposite of the heat of fusion. Melting and freezing, same change, just energy going in the opposite direction. You can do the same thing with vaporization. How many kilojoules of energy are required to boil 225 grams of ethanol? Okay, so again, there's no temperature data, so I cannot use the equation that has delta T. Instead, if there's no temperatures, look for a phase word. Kilojoules required to, there she is, boil the ethanol. So boiling is heat of vaporization. Any change that goes from a liquid to a gas. We're going to need moles. The equation is essentially the same as for melting and freezing. We're just going to look up heat of vaporization instead of heat of fusion. 225 grams. Ethanol's formula is C2H5OH. I probably would have given that to you. We need to get it out of grams and into moles. The periodic table will give me the mass of a mole. We just need to add them all up. 2 carbons. There's really a total of 6 hydrogen and an oxygen. 46.08. We'll divide, and I think we're looking at around 4.88 moles. I'll go 3 sig figs because the original mass was in 3. All right, so here we go. Delta H, change in heat. And yes, there is a change in heat even though the temperature is not changing. We're doing a major phase change here. Moles, 4.88. And then heat of vaporization is a constant that you find on a chart. All right, let's find it. Heat of vaporization for ethanol. 38.6 kilojoules per mole. Do you see the equations are almost the same thing? You just look up a different constant depending on if you're going between liquid solid or liquid gas. Well, that's not so bad. All right, so it was 38.6 kilojoules per mole. I have almost 5 moles, so it makes sense. I'm going to multiply. If I leave the same, like 3 sig figs, 188 kilojoules. This makes sense. I have a positive delta H because boiling is an endothermic change, and I should have a positive delta H. It's energy that must be absorbed. Pudding number 4, I want to know the energy change that would result when 50 grams of water vapor condense. So again, no temperatures, but then I'm looking for a phase change. Condense. Well, if I want to take the gas vapors and condense them back down to a liquid, I need to remove energy. This is an exothermic change, and I should get a negative delta H. So kind of like what we said for heat of fusion, for condensation, we're just going to use the opposite of the heat of vaporization. So this is for vaporizing or boiling, but if you want to do condensation, we just say delta H equals moles times, I'll squeeze it in, opposite of the heat of vaporization. That's for condensation. Same change, the energy is just going in the opposite direction. Which means that I do need moles. And actually, we already calculated that, didn't we? 50 grams of water, 50 grams of ice, which it's 50 grams of water molecules, and regardless of its phase, the molar mass is the same, whether it's solid, liquid, or gas. 1 mole is 18.02 grams, so whether I have 50 grams of ice or I have 50 grams of water vapor, they're both the same amount of moles. Let's get after this one. Delta H equals moles, 2.77. It's the same. I'm going to look up the opposite of heat of vaporization. So that'll come off this chart. I'm going to go negative 40.6. I like this. Negative 40.6 kilojoules per mole. And so we'll just multiply. My answer will come out in kilojoules, negative 112 kilojoules. Exothermic, energy being released. So again, if you're trying to decide, this is easy because it tells me on top what equation to use. But if you've got problems that are jumbled and you're trying to decide what equation to use, first, check and see if there's any temperature data. If you see degrees Celsius, you're going to use mass times temperature change times specific heat, which you'd look up on a chart. If there is no temperature data, then you're probably doing a phase change. If you're doing the change between solid and liquid, it could either be melting or freezing. You're going to do moles times heat of fusion, exothermic for freezing. If you're changing between liquid and gas, whether it's boiling, vaporizing, evaporating, or it could be condensing the vapors. You'll look up moles times heat of vaporization, and you'll just make this negative or exothermic.